Now we'll introduce a new definition and do a proof involving it. So the new idea that we're going to talk about is divisibility. So suppose a and b are integers. We say that a divides b, which is written like this: a divides b, if b is equal to 8 times c for some integer c. Okay, very important. This is not divided by. This does not mean a divided by b. It's not an operation. It's a statement saying that a divides b, that a has the ability to divide b. And the way we know that a divides b is if b is equal to a times c, where c is some integer. In this case, we also say that a is a divisor of b. Or we can say that b is a multiple of a. So those are all equivalent ideas. So some examples. So 5 divides 15. Right now this seems intuitive, I think, because if you have 15 and you divide it by 5, you get an integer, right? So 5 divides 15, meaning, again, 15 can be divided by 5. But let's see how it fits into the definition. 5 divides 15. So what are we trying to do here? So 5 is our A, 15 is our B. We're trying to find that 15 should be equal to 5 times C, where C is an integer. So again, we're trying to look for B is equal to A times C. So that is true, since 15 is equal to 5 times 3. 5 times 3. This is our C here. So now, since 5 divides 15, we also say that 5 is a divisor of 15. We can also say that 15 is a multiple of 5. So notice the numbers are now switched around. 15 is a multiple of 5. Okay. But 15 does not divide 5. So 5 divides 15. So the order matters. 5 divides 15. But 15 does not divide 5. This symbol means does not divide. 15 does not divide 5. The intuitive idea is that if you would take 5 and divide it by 15, you would not get a whole number, right? You would get a fraction. But let's see how it fits with the definition. 15 does not divide 5, since there is no integer c for which 5 should be equal to 15 times c. Right? There is no integer c that would make this equation work. Therefore, 15 does not divide 5, since there is no way to make this equation true in order for c to be an integer. 6 divides 6. That is true. 6 divides 6. Why? So here a is 6 and b is 6. Since 6 is equal to 6 times 1. So we have b is equal to a times 1. The point is 1 is an integer, whatever. It's b is equal to a times some integer. And in this case, it's 1. So therefore, 6 divides 6. Negative 6 also divides 6. So again, here, let's see. Here, our a is negative 6. Our b is 6. So we need 6 to be equal to negative 6 times an integer. Let's see if we can do that. And we can. 6 is equal to negative 6 times negative 1. Negative 1 is an integer, so this works. Okay, now let's do a proof involving divisibility. So here's our proposition. Let A, B, and C be integers. And when we say let A, B, and C be integers, what we're saying is this applies to all integers. Okay, we're not picking specific integers that it should work for. So you can prove this by giving an example. Rather, this is a statement that we're claiming is true for all integers A, B, and C. As long as they're integers, if A divides B and B divides C, then A divides C. For example, this says, that if 5 divides 15 and 15 divides 45, then 5 divides 45. Right? A divides B and B divides C, then A divides C. So this is, of course, you can give some examples, but that's not going to prove it. We want to prove that this is true for all integers A, B, and C. All possible integers. that we might choose. So here we're going to do a direct proof. So as usual in a direct proof, we start by supposing that this part is true, that the if part is true, and our goal is to show that the then part must be true as well, that the if part forces the then part to be true. So in other words, the last line of the proof, we expect it to be something like, therefore A divides C. That's our goal. Okay, so we're starting with suppose A divides B and B divides C. Now, what does that tell us? If A divides B and B divides C. Well, here we go back to the definition. And remember that even though definitions are written as even though it's written as if B equals AC, then A divides B, but really remember, we understand it as a biconditional, right? So if I tell you that A divides B, then you can know that B is equal to A times C for some integer C. So our next step in the proof is going to say, since A divides B, based on the definition of divisibility, we know that there is an integer D such that B is equal to A times D. Now, why did we use D? Why do we use integer D and not C? The answer is that we already have a different C in this being used in this proof. Right? So we have to make sure not to get confused or not to reuse variables that have a different meaning. Right? So A, B, and C were the three original integers. We are now introducing a new integer D, such that B is equal to A times D. So the point is, D is a new integer that we're introducing now. It's not one of the original ones, so we cannot use C instead in the place of D, right? So we have to use a new letter. So we'll use D. Okay, so that takes care of A divides B. What about the fact that we know that B divides C? Well, since B divides C, there is an integer E such that C is equal to B times E. Right? That just follows from the definition of divisibility. Now, again, why did we introduce a new integer here? Well, because it's not necessarily true that the same integer that divides, that the same integer that we're using here is going to be used here. In other words, it's not necessarily the case that this integer here is going to be the same as this integer here. Maybe they will be the same, but they're not necessarily going to be the same. So we have to introduce a new integer, a new variable here, right? Because we have to account for the possibility that it's in fact a new variable. Now it's possible that it's really the old one, but that's fine. You're allowed to have two different names for one variable. Sorry, you're allowed to have two different names for one number, right? So it's possible that they're both representing the same integer, but it's possible not. That's why we need to have two different names. So again, it would not be correct to say there is an integer D such that whatever, because we already used D for potentially a different integer, right? So if we're introducing something that might be new here, we have to use a new letter. Okay, now our goal is to show that A divides C. In other words, we're trying to show that C. How are we going to show that A divides C? We're going to have to show that C is equal to A times an integer. Let's say A times X. So let's figure out what C is. Well, we know C is equal to BE. So we know C is equal to BE, but we know what is B. That's A times D. B is equal to A times D. So let's rewrite this as follows. B is BE. So C is equal to BE, which is equal to A times D times E. Right? Again, B is the same thing as AD. But now we can rearrange the parentheses because it's just multiplication and multiplication. So we can do it in any order we want. So this can be written as A times, and then in parentheses, D times E. Now what do we have? Look what we have now. We have C being equal to A times X, where X is the integer DE. Look what we have, right? Again, we show that C is equal to A times an integer. DE has to be an integer because D is an integer and E is an integer. So, and multiplying two integers gives us a new integer, gives us an integer. So A A times DE is like A times X, where X is an integer. So what have we done? We have shown that C can be expressed as A times an integer. In other words, A divides C. Because what does A divide C mean? It means that C is equal to A times an integer. That's exactly what we've shown. C is equal to A times integer X. Therefore, A divides C. So what have we shown? We've shown that by supposing this to be true, meaning if we have this condition being true, that forces this part to be true. So that proves the proposition.